All right, wrapping up chapter 3 here with 3.7, looking specifically at residual plots and using those to see if our linear regression line is a good model for what is going on based on seeing what we see within the residual plots. And so looking at the data here, we have several sales for old school iPhone models during their opening weekends. You can see going all the way back to the original to the most recent on this data plot is 2015. So for some of you, not too much after you were born, so probably need to update this one at some point. But what I've gone and done already for you is I've used Statplet to plot the scatter plot and then create our least squares regression line there. And so looking at that, let's go ahead and do number 2. So we want to describe the form of the distribution. So remember, that's our Duff's. All right, so D is direction, U is unusual features. Are there any clusters or gaps? Form, right? Is it linear or non-linear? And then S is strength. Okay, so we're just looking at form. So in this case, this does look linear. All right, got a line there, decently fitted to that scatter plot. And so you can see we have our least squares regression line already, and then the equation that we get from that. All right, in context, so iPhone sold. So hat, because that's our predicted model, is going to be equal to negative 3,222.6 plus 1.60 times year. So we made our LSRL. A new graph was shown under our scatter plot. The vertical axis is labeled residual. And this is a sketch of our residual plots. Okay, so you can see here, here's our residual plot. Okay, so you can see our residual plot there. And as we look at this, you might see a pattern in our data. So there's what we call a left over curve in the residual plot. And when this happens, that means our LSRL, our least squares regression line, is not an appropriate model. Okay, so linear regression is not always the best fit, even though it may look close to what it was, because when we go back up here, that doesn't look like a terrible fit for us, but there may be a better fit. And so perhaps there is a regression model that is slightly better. And so we're going to look at creating a quadratic regression model, and we'll see what that plot gives us. All right, and so before we switch it over, though, I want our S value, so that 1.443 to be recognized. We're going to be using that later to talk about some things. But then down here, you can see we can calculate other regression models. And so there's quadratic and exponential. We're going to use quadratic here. It gives us an S, and we'll talk about that here in a little bit, but you can see for our linear one, it's 1.443, where for our quadratic one, it is 0.676. You can see that equation, we have that squared at the end. And as we come back up here, you can now see that scatter plot with that regression line is a much better fit, as you're seeing that spacing, and that is given even more credence when we look at the residual plot there of a quadratic regression model. All right, so you can see here the difference in the linear regression model had that leftover curve that you can see here, where here we're now above, below, above, below, above. You kind of have this up and down, where again over on our, we're above, then all below, and then all above, which lends itself to that extra curve. Right, and so remember our S value for linear was 1.443, and for quadratic was 0.676. Well, what does that S stand for? That S is the standard deviation. All right, if we remember back to previous, standard deviation is the average distance from the mean, okay, or where we can find our typical value. So now this is the standard deviation of residuals. So this S value is the average distance of our data points from our regression model, whether it's linear in the first case or quadratic in the second case. So the smaller the S value is, the closer we are to the mean and regular standard deviation. And in this case, the smaller the S value, the closer we are to our residual line, whether it be linear or quadratic. So the smaller the number, the better the fit it is. So in this case, we can see that quadratic, which is a nonlinear, but just another way to model it, is a better fit. Okay? And so for our interpretation of this idea, we'd state that the iPhones sold are typically about $0.676 million away from the predicted sales. And this right here would be when asked for your interpret S, or your standard deviation of the residuals would be essentially your sentence frame there. So context, all right, what is the S value, right? Typically is important because that brings into that definition of standard deviation, and then it's typically away from some other key things. Make sure you're talking about predicted sales. Okay, because this is coming off our predicted values, our linear regression line or quadratic regression line. That's a predicted value. All right, so let's formalize that. Okay, so these are relatively straightforward. We're talking about residual plots. So if it's scattered, we're up and down between it. We know that whatever the model is chosen, whether it's a linear or nonlinear model in the quadratic or exponential, it is a good model. If we have some kind of leftover curve, then we know the model chosen was a bad model. And then S is our standard deviation of residuals, again, which is just the typical value or the average distance from our regression line. And then our sentence frame we'll use there for interpretation is the actual, whatever our y variable is. So in previous, right, that was iPhone sold, is typically about s, whatever that number is, away from the predicted y variable for the model. Okay, and the goal always is to have a lower s value. Nice thing with Staplet, you can play around looking at the linear and compare it exactly to a quadratic or exponential and see how that all fits within that. And then real quick, going back up to here, we have r squared for our purposes. Okay, we're not going to worry about our r squared. We're just going to be focused on the s of that. Okay, so how'd you go and try these problems down here? So look at 1 and then 2 within that. Don't worry about 3 since that's talking about r squared. All right, so context here. So can you predict the battery life of a tablet using the price? So using data from a sample of 15 tablets, we have a least squares regression line where y hat is equal to 4.67 plus 0.0068x was calculated using x as our price and y the battery life. And we're given the residual plot. So looking at this for number 1, does the residual plot determine if our regression model is appropriate? And I would say yes, due to the residual plot being scattered. As we're looking at this, right, we're above, then below, and then above, and then up, and then down, and then back up. So the scatter plot is kind of all over when we look at the residuals, which means it's a good model. Okay, so with that, since it is a good model, let's go ahead and interpret the value of S, or standard deviation of the residuals, is 1.21 for this model. And we will write the battery life, and this is just following our sentence frame, is typically 1.21 hours away from the predicted battery life for the model. Okay, and again, looking at the things we institute, okay, y variable context, our actual S value with units of measure on it, and then don't forget this idea of typically away from the predicted. That's kind of our definition of standard deviation of residuals built into our sentence frame there. And no dad joke this time. Just curious to see how long you would wait or how many would go check the end to see if there was a dad joke waiting for you. So if you made it this far, though, I do appreciate your perseverance and your willingness to hear some crazy dad jokes. All right, kid, there's a dad joke here for you. This is for all my fans of one of the best Christmas time movies, Rudolph the Red-Nosed Reindeer. So what do you call a snowman with a six-pack? An abdominal snowman. Have a great one.